I welcome you to this class of econometric methods. I am Dr. Muhammad Imdadul Haq, an associate professor in the Department of Economics at Aligarh Muslim University. In our previous session, we were discussing about multicollinearity. We have covered a lot of ground like what is multicollinearity, what is the problem, nature of the problem of multicollinearity, and what leads to multicollinearity, then detection of multicollinearity. We have gone by stepwise and the Farrar-Glauber test. Today we will be discussing the remainder of the topic, that is, and we will start with the consequences of multicollinearity. See, what is multicollinearity? When there is a relationship or a perfect relationship between a perfectly linear relationship between the independent variables. Now, if the correlation between these explanatory variables is perfect, that is, the correlation between say Rx, Xi and Xj is equal to 1, then two things happen. The first, the estimates of the coefficients are indeterminate. And second, the standard error of the estimates become infinitely large. We will have a demonstration of it. Take a model, a simple a model with two independent variables, x1 and x2. Now, in the case of these two independent variables, and we assume that there is a linear relationship of this form, that is, x2 is a certain factor k of x1. Now, we have seen in our earlier cases the formula for b1 hat and b2 hat. So, what we are going to do is, we are just going to insert kx1 wherever an x2 is available. So, when we do that, we can see that when we have inserted in place of x2, we have inserted the term kx1, 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 kx1 and kx1. When we have done that, so upon algebraic manipulation, what happens, we can take k square common and we get this term, then we can get k, again take k square common. So we see that, and beneath it is k. So this entire term, this term and this term, it turns out to be same. The same thing happens with the denominator. As it is visible over here, if you can see that this term is the same as so beta 1, you cannot estimate beta 1. Beta 1 is indeterminate. Same thing happens over here. Now we take the beta 2. Now when we are taking beta 2, again what we are doing, we are simply in place, we are assuming the same linear relationship, x2 is equal to kx1, and again what we are doing, we are inserting kx1 in place of x2, in place of x2, in place of x2, in place of x2. Now, again, upon algebraic manipulation, we find that this term is just similar to this term. That is, the first term is k bracket open small x1y bracket close bracket open small x1 square, and the second term is also same, minus k summation bracket summation x1y bracket close bracket open summation x1 square bracket close. So these two terms are the same. So the numerator, it becomes 0. The denominator, it can be again written as in the format k square summation x1 square minus the second term is k square summation x1 summation x1 square. So these two terms are the same. So what we can say, the estimate of the coefficients are indeterminate. The parameters are indeterminate and there is no way to find the value of the coefficient. So this is a glaring example of the problem which multicollinearity can create. Let us take another case. Now we are discussing the second issue that is created, and that's the standard error becomes infinitely large. We again take the same the same multiple linear regression model with two independent variables x1 and x2. We assume that x2 is equal to kx1. Now if you take the formula of the variance, now this is the formula of the variance. This is the formula of the variance, and what we are doing, in place of x2 we are writing kx1, x2 we are writing kx1, x2 we are writing kx1. When we are doing this again, so the numerator is okay, fine, but the denominator, you can see these two terms in the denominator, they become the same and there is a minus sign in between. The first term is summation x1 squared summation kx1 squared, and the second term is summation x1 squared summation kx1 squared. So when these two terms are same, it becomes 0. So finally you can say the variance of beta 1 hat is infinite. The same thing, let us see it for the variance of beta 2 hat. Again you can see, we just insert wherever there is an x2, we insert, whenever there is an x2 we insert kx1, wherever there is an x2 we insert kx1, and again the term in the denominator is summation, the first term is summation x1 square summation kx1 square, and the second term with the minus sign is, and the second term is summation x1 square summation kx1 square. Now there is a minus sign between these two terms, so that is also equal to 0. So the standard error becomes infinitely large. So the variance of the estimates, they become infinite. So now once we have seen, we have identified what is the nature of the problem, what is the consequence of the problem. Now we can go for, okay, if after all there is a problem, what is the solution to it? A very interesting solution is, some suggest that if it is not severely impacting your model, ignore it, tolerate it. And a related one is, if somehow you come to know that this multicollinearity is because of a particular variable which is not very important, simply exclude it. So these two, we can say, we can simply get rid of the problem of multicollinearity, or if you can tolerate, just accept the problem of multicollinearity. Then the next solution is, we are going to increase the sample size. See, multicollinearity is a sample phenomenon. We have seen it earlier in our discussion. So simply by increasing the size of the sample, the problem of multicollinearity can be either reduced or say eliminated. See, here we have the variance of beta 2 hat, we have just written is sigma square divided by summation x square x2 square multiplied by 1 divided by 1 minus r square of 2 3. Or the variables 2 and variable 3. Now as the sample size increases, what will happen? The size of summation x, the size of summation, as the number of x is added up, summation x will increase. The moment summation x increases, the variance, because it is in the denominator, the variance will become small. When the variance decreases, it means it will lead to a decrease in the standard error, and that will enable us to estimate the coefficient more precisely. So one solution is, we increase the size of the sample. Next, say if we have a priori information, if we know something beforehand, like an example is written y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui. Now, if we somehow or the other we know that beta 3 is equal to 0.2 times beta 2, it may be say, if it may be that one of them is income and the other one is wealth. So we know that there is a relationship between, we can say that there is a sort of relationship can exist between these two, or we take any other example. If this happens to be the case, if we are knowing that there is a definite relationship, if we know that there is a particular relationship between variables, so what we do now, in this equation, instead of beta 3 we write 0.2 beta 2. Instead of beta 3 we write this term. Then what we do next time, we can see that we can take beta 2 common. So we have beta 1 plus beta 2 on bracket x2 plus 0.2 x3 plus ui. So we can now assume that x is equal to this term, x is equal to x2 plus 0.23. So now we can obtain the value of beta 1 and beta 2 from this equation. We obtain the value of beta 1 and beta 2 from this equation and the value of beta 3 from this relationship. But this is again a case wherein you must have a priori information. You must know from previous literature, from previous empirical works, that a certain relationship exists between two of the variables. So having a priori information is also a solution to multicollinearity. Now another solution is, we have two types of data. Cross section, where a particular information data has been collected at a point of time, and then we have time series data where it has been collected over a period of time at particular fixed or say at particular interval in time. Now suppose we want to study the demand for mobiles in Aligarh, and assume that we have time series data on the number of mobiles sold, that we can take it as say D, and the price of the mobile that is taken as P, and the consumer income that is Y. So our aim is to estimate the price elasticity, that is the coefficient of P, and income elasticity, that is the coefficient of Y. Now in time series data, the price and income variables generally can be correlated. So therefore what we do, we run the model OLS. If you run the model by OLS, you will get this problem, multicollinearity problem. Now if we have this cross section data, we should first estimate say the income elasticity, that is the coefficient B3 over here, the income elasticity, because see in such type of data, because this is cross section at a particular point of time, the price will not vary. So assuming this cross sectionally estimated income elasticity, we can estimate this relationship, where dt asterisk is equal to dt minus b3y. Now once we have done, now we can estimate the price elasticity, that is the coefficient of the variable P, that is B2, by OLS using the time series data. But obviously this is one of the methods to get the solution, but again it has its own limitations. Particularly it can be that we are assuming that the income elasticity is same at the estimated from time series data, but it may not hold true. But the thing is, this is one of the solution to multicollinearity, and we apply different solutions to different cases. For some it may be applicable, for some it may not be. And one of the most, I think, dropping a variable if we know that this is creating a problem. The simplest method, that is when we face high multicollinearity, is to drop one of the collinear variables. We come to know that x1, x3 and x4 are related. We can drop either x3 or x4, whichever you think is of relatively lesser importance. But this again solution is prone to a serious issue of specification bias. And dropping variable from the model, we may be committing significant specification bias, which arises from incorrect specification of the model. If for So it is not exactly like, take an example. Economic theory says that income and wealth should be included in the model of consumption expenditure. If you are trying to study consumption expenditure, both income and wealth, and if you are saying that okay, the data for wealth is having a relationship with income, so let us drop the variable wealth. But okay, you can drop it, you can solve a problem of multicollinearity, but it leads to another problem, that is of a specification error. Again, another interesting solution to multicollinearity is taking the ratio of it. See, we can take this that CO2 emission is a function of the economic growth, GDP, urbanization, energy consumption, and population growth. So this is, you can prove your EKC environmental Kuznets curve using this relationship also. That is, okay, we will move to the realm of your non-linear regression in the later classes, but at the moment we can also use this. So at the moment, let us assume that this is just a linear relationship. Now, if we know that somehow energy consumption or urbanization and population are correlated, say energy consumption and population are correlated, one way is that you divide the entire equation by one of the meaningful variables which can be got from here, like population. So we can say we divide CO2 by population, so we can get emissions per capita, GDP divided by population, GDP per capita, urbanization divided by the total population, that is urbanization ratio, and energy consumption divided by population, that is energy consumption per capita. So what happens is, you have as such removed one of the variables which was creating issues and also incorporated its effect by taking it as a ratio term. So this also, when you are taking a ratio of a term which was a variable which was having a collinear relationship with other variable, so this is also a solution to multicollinearity. Another solution is the method of first difference. So you can again take this one also as a solution. See, you have this equation yt is equal to b1, yt is equal to b1 plus b2 xt plus b3 x3. Now see, what the basic logic is, if this relationship holds at time t, then it will also hold at time t minus 1, because anyways the origin of the time is arbitrary. So therefore what we do, we take a one period lag. So for yt, you write it as yt minus 1, this is a constant, beta 1 is constant. For xt, you write it as xt minus 1, x3t, you write it as x3 minus 1, ut, you write it as ut minus 1. So we take a one period lag. So this is, if you, it's very simple, like if you have a variable like x, 2, 5, 7, 10 and 15. This is say xt, I want to take xt minus 1. So simply what you do, here there is an x, there is nothing, but this 2 you can write to the other period, this 5 you can take here time, say it is 2001, 2002, 2003, 2004 and 2005. This 7 you can write over here, this 10 you can write over here, and you can create another variable xt minus 1. This is nothing, we will cancel this one, we will ignore this. 5 minus 3, 2, 7 minus 5, 2, 10 minus 7, 3 and 15 minus 5, 15 minus 10, that is 5. So we can create so this is one way of minimizing the dependence, is to proceed with this first order difference equation. And then once we do, then we do yt minus 1, yt minus 1. So what happens, b1 minus b1, beta 1 minus beta 1, they cancel each other. Now here you take beta 2 common, then you have x2t minus x2t minus 1, and similarly you take b3 common and you have x3t minus x3t minus 1, and again you take the last term ut minus ut minus 1. We just assume that this ut minus 1, we assume it by a term vt. So we have this yt minus 1. We can write this as beta 2 bracket x2t minus x2t minus 1 plus beta 3 bracket open x3t minus x3t minus 1. So say we have a time series data on consumption, expenditure, income and wealth. Both income and wealth move in the same direction over time, which will obviously lead to the problem of multicollinearity. Now, when we are taking the first order difference equation like what we have seen over here, it reduces the severity of multicollinearity, because see, although the levels of these x2 and x3, these levels of x2 and x3 may be highly correlated, but there is a reason to believe that their difference will not be as highly correlated. Like when we have taken the difference, it will not be the degree of correlation between those variables uh, will be gone. But again, this is again a method to solve the problem, but again it has its own limitations. The moment you are doing the differencing, you are doing away with all the long run properties of the relationships. All the long run characteristics is gone. You are just taking two period. You are just studying today's period with the last year period. So again, that is another issue which arises because of this. The next method is simultaneous equation. We can go to the realm of simultaneous equation model. Say multicollinearity, and an example of simultaneous equation model is given. You have this your basic y income in y is equal to c plus I. We have ignored g at the moment. Y is equal to c plus I, and we have a function of c and you have a function of I. There are things that income is coming into both the equations, in the equation c and equation I. That's a we will discuss this when we discuss the case of simultaneous equation. But for now, multicollinearity arises due to the dependence upon the variables, which may lead to endogeneity issues. Endogeneity issues, at the moment you just understand uh, yt is, it's coming in both the places. Yt is also an independent variable and also yt is as a dependent variable at a place. Now the simultaneous equation models are treated as jointly determined, meaning that the model accounts for the simultaneous relationship between variables. So by explicitly modeling these interdependencies, a simultaneous equation model can help disentangle the relationship among variables and reduce multicollinearity. So as in this simultaneous equation model, all equations in the model are estimated simultaneously, taking into account the relationship of the variables. Now this approach allows the model to allocate variation among correlated variables more efficiently, and that potentially reduces the problem of multicollinearity as compared to when you are taking each of the equations separately. But again, we have to look for other things also, like you have to check for the simultaneity bias, you have to check that the model is identified or not. And in fact, we will be doing simultaneous equation model in detail. We have a syllabus, we have this topic in our syllabus. The next way out is principal component analysis. Principal component analysis is can be defined as a dimensionality or reduction technique used to transform high dimensional data into lower dimensional space while preserving most of the variability in the original data. Uh, you can understand by a simple example, like you are trying to study you are trying to study how a car, which car is you prefer, which type of car, or which car is better or not. So now if you identify the characteristics of a car, say you have some like power, you have that say power, torque, then you have engine size, and these things and acceleration in we reach in 60 miles 60 kilometers per hour in 2 seconds, these things. Then you have certain things like how many airbags are there, what is the braking system is there, ADS sensor system is there. There can be many things. Then again you have some things like um, leather seats are there or not, how is the front grille, back grille. And then you have other things of aesthetics like say the color, it is dual tone or not, you have sensor wipers or not, and these things are. Now if you are studying all these, and there can be many more, I have just cited few of them, and if you study all of them together, so many variables, there is a high chance of getting something, getting a collinear relationship between any of two of the variables. So what is this, what this method does is, in crude terms, in basic terms, it tries to convert these power, torque, engine, acceleration, because they are related to the power of the vehicle, into one variable, say x1. The remainder, that is the braking system, airbag, ADS, this is as x2. And the remainder like the color, the seat and the sensor, the moment I go into dark, the light automatically goes up, these things as x3. Now basically what we are doing, we are reducing the number of variables. So this principal component analysis transforms the original variables into a new set of variables known as principal components, which are linear combinations of the original variable, because this will be related to all this, this will be related to all this, and this will be related to all this. And see, these principal components are orthogonal to each other, meaning they are uncorrelated. They will, okay. Or in the simple terms, we can say principal component analysis, it reduces the dimensionality of the data by retaining only a subset of the principal components that capture most of the variability in the data. That is the beauty, that although we are reducing the number of variables, number of items to be studied, but at the same time we are not we are capturing as much variability as we can. So by this selecting a smaller number of principal components, this effectively reduces the number of predictors in the regression model, thereby reducing the risk of multicollinearity. So today, as such, we have completed the topic of multicollinearity. We have seen this is a common issue which happens when there are a number of independent variables, and then we have seen what is the nature of them, what happens because of it, what is the nature of the problem, and then we have moved on to how can you identify the problem, and then we have discussed many ways to solve this problem of multicollinearity. Hope the lecture was clear to you. Thank you.